somebody needs follower, please follow this person on IG. Hello everyone, welcome back to another week. It's week 4. So, what will be the final exam format? Final exam format will be theory, coding slightly. Yes, theory and coding, both. Do we have midterm? Yes, we have midterm. Nobody remembers what regression is about. Regression is used for regression tasks. Yes, correct. How can I deny that? Regression is a supervised learning algorithm used to figure out trends. Yes, correct. What trends? I remember logistic regression, multiple linear regression model. Okay, thanks for remembering. Modeling algorithm used for price prediction. Yes, that's correct. Simple and multiple linear regression. Yes, that's correct. Regression model is a statistical method. It uses a straight line. It uses a straight line or a plane to estimate the relationship between independent variables and dependent variables. Yes, it's correct. The exam you said theory and coding is for mlpc and CB/NLP. Yes, correct. Can I use dataset that contain fabricated data in my assignment, or must the dataset have only legitimate data? How fabricated is it? Can't you use legitimate data? Depends on how fabricated it is. If it is clean, I think that's no problem. But if it's entirely fabricated, I don't think that's a good idea. Midterm on week 5? No, definitely not next week. Regression model is a supervised data model which can be used for price prediction. Yes, that's correct. Is it a one-day midterm, or how long will the midterm take? Probably a few hours, which you can initiate anytime that you prefer. What should be written in problem statement of assignment 1? Problem statement of assignment 1. It should be something which justify that the task is difficult to be conducted by humans and therefore requires machine learning. If I create my own data, why would you spend time creating your own data? Spend time doing your project. Because I don't have a URL link for my dataset, I export the data. I don't understand. You should be spending time doing your project, doing your literature review instead of creating your data. Don't waste time doing your data. Okay, welcome back, class. It's week 4. So this week we are going to talk about something really technical into our first machine learning algorithm, which is called the regression. Okay. So now I asked a question about what you remember about regression model. I think everyone have said something which is correct. So it is used for regression task. Yes, that's correct. Regression is a supervised learning algorithm used to figure out trends. Okay, that's also correct. Regression model is a statistical method that uses a straight line or a plane to estimate relationship. That's also correct. Regression model is a supervised data model. which can be used for price prediction. That's also correct. So I think everyone is correct. Is the midterm going to be held next week? No, definitely not next week. Yeah? Okay, so somebody is asking for partners. Partner in crime. So, yeah, there you go. Hello, welcome back everyone. Today we are going to talk about regression. So we'll be going through some very technical aspects of regression, which covers linear regression as well as multiple linear regression. Yeah? Just a recap of what have we discussed about regression. So in week 2, we sort of discussed that regression is actually a machine learning algorithm which constitute a line. Yeah, so this line is a regression line, which means that is our regression model. And there are many types of algorithms that can be used for regression tasks. And today we are going to discuss the first one, which is linear regression. So a common use case of regression is usually for price prediction in many, many domains. So this is what we will be talking, what we have been talking about. So for today's lecture, we will go through linear regression, which will talk about what are the machine learning parameters. So machine learning parameters for linear regressions include the two main parameters, which are the y-intercept, beta naught, and also the slope, beta 1. Then we'll also talk about how do we teach this algorithm to find the best fit. So as for human, we can just draw a line among the dots and say that, oh, hey, this is the best line, best fit. This line best describes all the points in the data set. But then how do we do that using algorithm to allow this computer algorithm to read them? So the underlying principles are sum of squared residuals, SSR, coefficient of determination, R squared. Yeah? So once we have covered this SSR and also R square, we will be talking about multiple linear regression. Okay? So after multiple linear regression, we will touch base on the performance evaluation metrics for regression model. So what kind of metrics can we use to say our model is good or it's better than one another? Yeah? So that's for today's lecture content. Let's get started with introduction to linear regression. So how do we start? So linear regression, yes, everyone have got it right. It is a type of model for finding linear relationship between the target response as well as more features. So bear in mind that for any regression task, whenever we say regression, our target response have to be referred to continuous variables. Continuous means things which are numbers. Say, for example, prices, temperatures, so far and so forth. Yeah? So we will always have one target on our y-axis, which we want to predict, and multiple features, which is also continuous in nature. Yeah? So say, for example, we have a feature which is numerical, and we are trying to predict a target based on the particular feature. What we need now is to collect data points that consist of this feature and its relevant target values. So once we have that target value, our regression task is then very simple, to draw a line that fit to all the dots. So put it in a simple way, building a regression model simply means drawing a line to fit all the dots in a plot, in a scatter plot. Okay? So that's about regression model. Simply just feeding a line to a set of data, which are continuous. Okay? So as for today's class, we will start with one basic simple example. So let's say we take a look at this simple data set. So this data set is a movie budget and revenue data set. So the problem here is to predict the box office revenue of a particular cinema. Okay, so now what do we have here? Say, for example, based this domestic total gross, here is the revenue. That means how much a cinema would make how much cinema would make from a particular movie. Budget means the advertising budget. Yeah, how much money do they have to advertise the movie? So for every single movie, if they have a certain budget, they are tracking on their revenue. So this is our data set. Aside from the budget and also the revenue, we also have other features like what are the movie titles, when is it being screened, who are the directors, what is the rating of the movies, and also how long is the runtime of the movie. So let's just take an example where we just want to predict the revenue based on the budget which is available. So what we do then is to identify our target response, which is our revenue. So our target response is always a continuous value, and the first feature that we have chosen is budget, which is also continuous in nature. So what we do then is to plot a chart that say if I have a certain budget, what is my expected revenue based on the past historical data which we have. So what we are trying to say is, okay, so now we have collected a set of data set historically. So in the future, we are assuming that if I spend a certain amount of time to advertise my a certain movie, I'm going to expect a certain level of return. So this is the purpose of this predictive model. Yeah? So far, so good? Okay. So this is the quick context. So I hope everyone is okay so far. That is just a quick introduction. So I suppose we shall move on. So the first thing that we are going to talk about will be the machine learning parameters. So what really defines a line? Because we know that regression is just about drawing a line, fitting a line across all the dots that we see on a scatter plot. So linear regression parameters. At the very simple format, the basic format, regression model just refer to one line. Remember that, one line. So one input value will produce one output. Yeah. So this line can be defined by this equation, a generic equation as what we see, which we will also take note on the two key parameters here. First coefficient is this beta naught, and the second coefficient is beta 1. So what is this beta naught and beta 1 is something that we will go through later on. And our regression model, in the process of building this regression model, we are trying to learn these parameters. Say, for example, what value would be the best beta naught, and finding out what value is the best beta 1. Yeah? So what is this beta naught and beta 1? So the two key parameters here are y-intercept and slope. I believe this is something which everyone have known. This is very basic, very simple. Yeah? We will take a look at the first parameter here, which is the y-intercept beta naught. So beta naught is the y-intercept, which is this value. So it is a point where the line, our model, cross the y-axis. So say, for example, what does this mean to us? It is a value that shows when the box office revenue is x is equals to 0, whenever we have no marketing budget. So say, for example, in any case, we have a movie, but we don't have money to advertise the movie. So this intercept, the value of this intercept will tell what is the expected revenue from that particular movie. Yeah? So that is what the y-intercept means. It is a point where the line crosses the y-axis. So then the next parameter which the machine learning algorithm is trying to learn is the slope. So this slope. So this slope tells us how much the y value will change for every unit change in x value. Say, for example, for every dollar of budget or budget allocation that we have or we increase, how much will the revenue increase? Yeah. So that is on the two parameters. A regression model is just a line. So this line is defined by a y-intercept and a slope. Okay? Question? In the linear regression equation, what does the B naught represent? Thank you for paying attention. Sorry, this is 1. If a linear regression model has a y-intercept of 5 and a slope of 2, what is the predicted value of the dependent variable when the independent variable is 1? Yes, that's 7. Thanks for staying awake. So now we talk about this y equals to beta naught plus beta 1x. So it is very simple mathematics which we have already learned from the secondaries. So now why are we doing this over and over again? So the point of doing this in the machine learning context is that we wanted to know how do we automate this task. So how do we allow the algorithm to learn this line? Yeah, we are not plotting the dot ourselves, but this time around we just want to make this machine do the task. So how do we get to this best fit line is essentially, I'm supposed to put a question here. So based on these 3 graphs of the previous problem, so what do you think is the best line? Which one do you think is the best line here? Is number 1, number 2, or number 3? So every single line here is referring to a model. So they just differ slightly by different y-intercepts and different slopes. Yeah? So now even human now is very hard to tell which model is the best model. So then how would a machine decide which line is the best fit line? So what it takes here to decide the best fit line using by algorithm means is to calculate a value called residuals. So these residuals will then be used to derive the sum of squared residuals. So what we need to calculate the sum of squared residuals as SR when the slope is 0 and the y equals to the mean of target, as well as when the slope increase or decrease. So now what happens whenever we start to train a machine learning algorithm, a regression model, used by any means is that, so now we say we have a set of data. So how it gets started is, the process will start with one single random line. So then it will go about and calculate, okay, if I have this line, I will calculate the distance of that line with the predicted values. And then it gets us the residuals. Yeah, it gets us the differences. So once it reaches a line which says that the total differences is the smallest, then it will stop and produce the line, which we will then be able to quantify the y-intercept and slope of that line. So now let's see how it works here. So how do we calculate the residuals and what is the residuals? So residual simply means the distance between the line and the data point. So now just take a look at a generic problem here, a generic scatter plot which look a little bit similar to our previous one. So now say for example we have some data points over here. how we get started with calculating the residuals is we will begin with a line when the slope is 0. So when the slope is 0 means the line is a horizontal line. So now the y is equal to the mean of our target. So say for example, our target ranges from this value to this value, and what is the average of the mean? So this is where we start. So now we draw a line that says, okay, y equals to the mean of the target. Yeah, let's say it's b. So y equals to b because the slope is 0, and therefore it is plus 0x, no x. Yeah. So the distance between this line, this point, and this point, this data point, defines the first residual. Yeah. So this value is b, and this value here is equals to y1. So this is the distance and the first residual. So now we will go about and calculate the distance between the second data point to the line. Yeah, to the line. So now we go about and calculate this value, b minus the value y2. Yeah. So here we will get the difference, which is the residual. So then we'll go about and calculate the third one. So this process keep repeating until to a certain point when this so it will just keep on calculating the residuals in order for us to get the sum. Yeah. So now 3 of the point here so far is helping us to is giving us some positive residuals because we are taking a bigger number, bigger value, divided by a smaller value over here. Because so far, all the data points are below the point that we're trying to predict, the mean of the target variable. Yeah. So now, when it comes to the fourth data point over here, fourth and fifth data point over here, we can see that the this point is bigger than the average. So when we take this difference between this point and this point, it will produce a negative value as our residuals. Yeah. So residuals here simply means the difference between our point and the predicted value. So now this negative value is not good. Why is it not good? Because as we add on the residuals of every single data point, comparing to the point of the model, it will then subtract and offset the residual from the rest of the data points. Yeah, so this negative value is not so good. So let's go about and calculate the residual of the next point. So on the next point here, we can see that it is also a value which is bigger than b. So now the residual here will also produce a value that is negative because we are taking this value, the mean of the target variable, divided by the minus the data point y5. Yeah. So then this negative value will grow bigger, which means that it will trade off the rest of the residuals which we have calculated earlier on, and the total residuals here will be 0. A residual of 0 means that the line is fitting well to all the data points. So that is a misrepresentation that we are looking at. So then, how do we go about in handling these negative values? So back in those days when the researchers are looking at this problem, there are always two ways of making a value positive. We can either take the absolute value or we can take the squares of this value. So in this case, for calculating the SSR, I wasn't too sure why, but it probably back in those days, some researchers were working on this problem, and they have probably been looking into how to make these values absolute. But it turns out that the math could be quite tricky if we were to use the absolute value, and therefore the recommended values here is that they end up squaring each of the residual term. So by squaring all of these residual terms, we'll then turn the negative residual values into a positive value. Yeah? So by turning this negative residual term into a positive value, that means whenever we add up the total residual here, it wouldn't trade off the rest of the residual, which are in positive values. Yeah? So now, the point that we are trying to get here is the sum of squared residuals. So this term here, where we're trying to add up the sum of the residual of each single data point to that particular line, is the sum of squared residuals. Yeah? So this is the sum of squared residuals. So now say, for example, we have completely calculated the residuals of each point to the line, to a particular line, to a model. So then we'll be able to produce a value, say for example, 24.6. So what this value represents now is how well does this line fit to the data. So now by taking a single value itself, it wouldn't tell us how good or how bad this line is. It is a relative values. Yeah? So now it is called a sum of squared residuals because residuals are the difference between the line, and we are taking the summation of all this value, and therefore this is where it gets its name, sum of squared residuals. So now, how do we then use these sum residuals? Say for example, our machine learning algorithm always starts with a horizontal line. So what we do next is, we are trying to tilt the line. Yeah, rotate the line by a little bit, changing the slope and also the y-intercept bit by bit. And for every rotation that it does, it will go about and calculate the sum of squared residuals of each point compared to the model, to the point that is predicted by the model. So say for example, this example here, whenever we rotate the line slightly into this line, we can see that the SSR would slightly reduce. So how can we see that from this illustration? We can roughly see that by, if we were to take the sum of this distance, this distance will be slightly lower than this one. Yeah, because we are trying to fit to the particular trend of how the data behave. So say for example, we just do another rotation, it will produce another line. So once it produces another line, we will go about at the back end of machine learning algorithm here, it will go about and tabulate the sum of squared residuals over and over again. So now say for example, if we are changing from 24.6 to SSR of 18.7, that means we are trying to improve the fit of the line. Yeah? So as we move on to rotate further, it will continue to improve the fit of the line because the value is lower than another. So when does a machine learning algorithm stop learning? It will stop learning when it reaches a lowest point and the next point gets higher. So that is a point where it will stop rotating. Yeah? So now say for example, if we just go about and rotate even further, we draw a very extreme line over here. So what happens is that when we calculate the residuals, it is going to be very extreme, extremely high, even compared to the original line. So based on this SSR, this is where the algorithm will decide which line is the best fit line and produce as an output for us. Yeah? So this is SSR. So now I mentioned about this process is an iteration process where the machine learning algorithm will just keep on rotating the line to a certain level. So what it does here is at the back end, it will keep on computing the sum of squares repeatedly. So if you were to look into these values as in the according to its rotation over here, we can sort of see a graph that behaves this way. So now say it just gets started with a straight line here, and then as it rotates, we can see that the SSR slightly reduce, improve. So now this model knows that it will keep on going on, rotating that line in the same direction. So as it continues to rotate, it will produce another point here. So as it continues to rotate more extremely, we can see that the SSR will increase because the line just gets further away from the predicted values. So now this model will then this algorithm will then be able to know which line at which rotation angle produce the best fit value. Okay? So the key takeaway of this session is the best fit line. The best fit line here always refers to the line rotation that has the least sum of squared residual. It has the lowest SSR. Okay? So what is SSR? This one requires some thinking. Which of the following statements is true about the sum of squared residuals SSR in linear regression? A value of SSR close to 0 implies a perfect fit of the model. Not so. A higher SSR indicates Okay. Minimizing the SSR is a key objective when we fit a linear regression model. Yes, that's the correct answer. A higher SSR indicates a better fit of line of the model to the data. No, that is not correct. SSR represents a variance in the dependent variable explained by the model. No, that's not correct. So it is minimizing the SSR is a key objective when we are fitting a linear regression model. So that is something that is happening behind all the algorithm of how this algorithm is able to produce one final line. Therefore, it is always very important to remove the outliers because those outliers in your data set is going to contribute to the calculation of SSR. So once the calculation of SSR is off, we know that it will impact how good the model is. Yeah? So the SSR is calculated by correct. Squaring the residuals. Residuals refers to the differences between actual and also predicted values. And then we take the sum of all the data points. Yeah. So now the next metrics that we are going to talk about that is very pretty much related to the measurement of this. The fit of a particular line is called the R-square. It is the coefficient of determination. So how do we derive this R-square? So a higher R-square value, which is close to 1, always indicate a better explanation of overall variance. So in any of our regression tasks, what we are trying to do is actually to increase the value of R-square. Okay? So in simple word, what is this R-square? R-square determines how good is the predictive power of our model. Yeah, how good is the guess of our model? So now, how do we go about and calculate R square, and what is this R square? So in order to calculate R square, we will need the variance. Okay, so we need the variance of two things. We need the variance of the target variable and to calculate the variance of the line, which is our model, in order to derive our R square. So now what does this mean? So on your left here, this graph shows all your target variable. And if let's say we were to have a line in between as the mean or the average of the target variable, so the SSR, which is the SSR here, will refer to the point or the distance of all the target variables of the target variable. It is the variance of the target variable. So now what is variance? Variance is the sum of square residuals, the SSR, divided by the total number of points. Okay? And R square is just the variance of target minus variance of fit divided by variance of target. So now how do we go about with that? So first of all, we need two things. So first of all, this one and our line. Okay? So now in this chart here, it will show us the variance of target variable. Why is that so? Because this line here represents the mean. Okay? So the mean means this one we are trying to calculate the variance of target variable. So how do we go about with that? So there are altogether 9 points here, and we know that our SSR is 24.6. Therefore, 24.6 divided by 9 is 2.7. This is the variance of our target variable. Yeah. So then we know our SSR of this particular line, which is 14.05. Then so then our variance will be 1.6 by when we take 14 divided by 9. Yeah. So now here what we get is a value of 0.4. So what does a value of 0.4 means of R square? So it means 40%. 40% means that 40% of this sum of square of the target can be explained by the feature. So now let's take a look at what it means. Yeah. So now when we calculate the variance of the target variable, what we are trying to say is how far off is all of this value apart if we don't have any features. By nature, what is the range of our target variable? Yeah. So the range of our target variable is about, the variance is about 2.7. Yeah. So then what we are trying to say is, if let's say we use this particular feature, let's say simply one feature, to try to describe the relationship between that feature and our target variable. So how many percent will this feature contribute to describing the trend? So here, if you were to add on one feature and it produces a R square of 0.4, it means that this feature can explain 40% of the variance in the target variable. Understand? You can, okay, understand? So that is not so good. So what is a good value of R square? The higher, the better. So a R square value will cover a range from 0 to 1. Yeah? So we are always targeting to arrive at a value of 75%. Okay? So now, what does a R square of 100% mean? R square of 1%. So now say we know that the variance of our target variable is 2.7. So then if let's say we have a line, that, we have another data set which we could fit perfectly, which we could fit our line perfectly across all the points in the data set. This will be a situation where our variance is 0. Yeah? So whenever our variance is 0, let's see how the R square will be reflected. Say for example, the variance of the target variable is 2.7. So when we take 2.7 minus a variance of 0, because they are fitted exactly to the line, so the variance is 0, divided by 2.7, this is how we get 1, that is 100% of R square. That means 100% of the variance in the target variable can be explained by this particular feature. Okay? So what does a R square equals to 0 would look like? So if let's say we have the same data set, okay, so now we know that the variance is 2.7. Yeah? So now the variance means the differences between the point in our target variable is 2.7. We are trying to find a feature that would describe the variance of the target variable. Say for example, we just simply pick one not so suitable feature over here. So what it does, what we observe here is that the variance still remain as 2.7 because we couldn't find a trend, a trend line that describe the pattern. So at the end of the day, if let's say our variance is also 2.7, so 2.7 minus 2.7 divided by 2.7, and therefore it's 0 divided by 2.7 and 0%. So we can say that this is a very bad model because 0% of the variance of the target variable can be actually explained by the selected features. Yeah? So how high or how low the R square is rely on how well the feature would describe the variance of your target variable. Okay? Got it? So R square is a measure of how well the variation of target variable can be explained by our line or our model. Okay? So the aim here is in a machine learning or a machine learning task of building a regression model is always to increase the R square. Yeah? What does a higher R square value indicate in linear regression? A higher average absolute error between actual and predicted value. A perfect fit of the model to the data. A larger unexplained variance in the dependent variable. A stronger linear relationship between the independent and dependent variable. The answer is B. It is not the higher average absolute value error between actual and predicted. No, it doesn't reflect that. It is the opposite of larger unexplained variance. Yeah, it is the opposite of this sentence. It is not a perfect fit of model unless the R square equals to 1. Okay, so now what we just go through is we have y equals to, we are trying to include one feature. So now say, go back to our previous case study here. We are trying to fit a line to predict the box office revenue based on the budget that we have. We can see that the dots here are pretty scattered. And using this feature, this one continuous feature alone, does not help us to predict the box office revenue very well. Yeah? If we were to produce a line that we see like previously, it is going to give us a model that will give us very high error, especially when our budget is high. So whenever our budget is high, we would be expecting the box office revenue to be slightly higher, but in fact, we may come to a point to observe an overestimated value. The actual value can be lower than the predicted value. So now what do we do is, we may need more features that could be affecting this trend. So say for example, what if this particular movie, even though we have thrown in a lot of budget, it is still very low? Could it be because the rating is of a certain class which limit the person who watch that movie? Could it be because people do not want to watch that movie because of the runtime? So then we may come to a point where we want to include more and more features into our linear regression model. So in this case, what we will be adding on is adding on more X into our model. So say for example, we have our initial beta naught, that is our y-intercept. So now we have our first variable x1, which is marketing budget. So now we just want to add on x2, x3, x4, x5 to xn. So in this case, we are trying to learn all of the beta that is relevant to every single feature, additional feature that we add in to this model. So in this case, what we will be looking at will be a multiple linear regression model, because we are using more than one feature to predict a particular continuous variable. Okay, so that is called a multiple linear regression. So in terms of multiple linear regression, it is as simple as defining what is our x and what is a y which we want to implement. And in next week's lab, we will be looking at how do we use this scikit-learn to train our multiple linear regression model. And then we will also go about and compute the coefficients, all of these coefficients using our Python code. Yeah. So finally, how do we define that how do we define the model performance? So as we look for literatures, we want to sort of know who produces the best regression model to predict a certain task. So then how do we do that? So there are a few performance metrics that can be used to measure the performance of regression model. So some of them include the MAE, MSE, RMSE, and R-square. We have just covered R-square earlier, but what are the other matrices here? So the E's over here refers to errors. So it is about the measure of how good is the fit and how high is the error the model would produce. Okay? So now the first error term here is mean absolute error. So the mean absolute error here measures the average magnitude of errors in a set of prediction without considering their direction. So what does that mean? So say for example, we have an actual values and we have the predicted values. So what MAE is then, what absolute error mean is we are taking the errors, then take the absolute value of the error. So this value over here is the absolute error. So now what is the mean absolute error? So now say we have a set of actual price, predicted price, we will be able to tabulate its error. So once we have that error, we will take the absolute value of each error. And at the end of the process, we will take the mean value of the absolute error as the MAE. Okay? So there's a difference between taking the mean of the absolute error and the error, because if we were to take this error, it will trade off certain values with its positive and negative signs. That is MAE. So now what is mean squared error? So mean squared error is simply taking the square of the absolute error. So the value can range from 0 to infinity. Yeah? So there is no cap to these values. So once we have the error, we have the absolute error, we will then square this error term to get the squared error. So once we have computed all the squared error, what we have here is the mean of all the squared error. So what is the benefit of this squared error versus the absolute error? So by taking the squared error, we are trying to add on additional weight to every error that this model is this model produce. So what it means here is it is very sensitive because we are penalizing this predictive model for every single degree of error that it has made. So in terms of training the model, MSE is always the preferred metrics whenever we want to train the model. However, whenever we are trying to read in terms of interpreting the differences, the error that is produced by this model, squared error can be something that doesn't make sense in terms of interpretation. And therefore, we go about and compute the next error term called the root of the mean squared error. So what is the root of the mean squared error? So the root of the mean squared error simply means we take the total of the squared error and then take the root of this mean value. And that is our root of mean squared error. So this is a more descriptive value of describing how much error does this model actually produce.